Okay, so getting started with all this, what's everybody's experience with TypeScript in here?
I would say like in between beginner and like mid. So
Okay.
Probably intermediate. I use it day to day at work.
Okay. Yeah, then that'll be different. I did it another time where some people hadn't tried JavaScript or hadn't heard of TypeScript even, so it'll be a different experience. We'll see. But that should be pretty good for being able to understand everything, I think. But, okay. I have to practice talking loudly too, so let me know if you can't hear me because that means the recording probably also can't. So for the purposes of today's talk, we are not going to do any runtime JavaScript. No JavaScript is allowed here. So for example, there we have some runtime code, which is not what we're after, but we actually want something like the bottom where we pass type arguments. We're going to use literals there. So 1 and 2 is a literal, will give us the literal type 3 as opposed to anything during runtime. And you'll see this here a lot, which is called a 2/, which just shows you the result of the type. And that is an extension, like in the TypeScript playground it'll be in there, and then as well, I have it in my own editor, but it's just good to show what exactly this type resolves to rather than guesstimating. So why do we want to do this? Since it's not very practical on its own, I think it's really fun in general, and otherwise it's really good to get an understanding of the type system. So we will see how impractical it is later on in a real world setting, but that's why I'm into it. So who is it for? We've already mentioned somewhat before, but as long as you have some programming fundamentals, and you should be good, but some JavaScript would be helpful, or some TypeScript experience would also be helpful. It would take a bit of TypeScript to be able to understand everything, so you need to know, like you'd have to write libraries with good TypeScript types, some complicated types to understand it all, and even then, some of it is very contrived, so come along no matter what experience level you're at. What are we gonna get into? So we're gonna get through generics and generic constraints, conditional types, map types, variadic tuple types, the infer keyword, recursion, and then finally our main event, which is type level addition. A lot of these sound very scary, I would say, and the reason I write them all down is because it's very hard to find out a lot of these things without knowing what the actual correct words are, like variadic tuple types. If you don't know what that is, then, and you know kind of what it is, it's impossible to look it up because whenever you look anything up, it will be superseded by the JavaScript version. Like someone asks, like, how do I get the last element of an array? You will definitely find the JavaScript version. They'll just tell you how to do that rather than how to do it on the type level. So it's unfortunate that we need to know these magical words, but they're here for a reason.
yeah.
So getting into generics, these are our parameters on the type level. So for example here, we have a practical example of an array. Arrays don't really care what they're holding inside because all they care about is, like in this case, pushing and popping and mapping over these items. It doesn't actually do anything itself. Like for example, in map, it's taking a function that takes a type u, returns a type, takes a type t and returns a type u. So ultimately, it does not care what's held inside. It'll do all of these things as normal. And here's a more fun example. We could take a slushy maker, for example, and in this case, we take in some kind of flavor and it'll return a slushy of that flavor. However, well, I always forget I had this slide, but it's here. So sometimes, like, why do we use TypeScript types in the first place? We care about some property of these types. So we want x and y to be numbers, because otherwise they could do various things. So for example, you could add bigints together, you could add it together booleans, you could add together strings, you could add together other things. Most of these don't throw any kind of errors. I think adding symbols would, but that's kind of weird. But either way, we care about some property of these, and we would like to know what exactly we're getting out of this. So equivalently, we can do this on the type level. Wow, this slide does not fit. Let me see if I can full screen that. Oh well, didn't work. But, so if we care about certain properties of a type, we'll use generic constraints. So here, for example, we take our flavors, we have a union of flavors. It could be lemonade, orange, Fanta, peach, whatever we want out of this list. And here, we can say this must extend the slushy flavor, which means that it must be assignable to this type. So it must be one of any of these, or the bottom type, never, which is a part of all unions. But, so like for example, if we had like a boolean, you could assign boolean to it, you could assign true to it, you could assign false, but some string called true would not work for that. So here we're pretty much saying, okay, we're passing all these flavors in, but if we try to pass in beans here, that is not a valid slushy flavor and it will not work. It is not assignable to that type. That all makes sense? Any questions? Okay. So, getting into some conditionals. On the type level, we don't have any if statements, we do have a ternary, but it works differently here. So we're talking about what we just mentioned, so anything assignable to that left part. So T must be assignable to that right part for it to become a true condition. So here, if T happens to be peach, then it will be false. We'll say it's not delicious. And otherwise, if it is delicious, we'll say true because it does not match peach. So, getting into an exercise for this, we want a type AND that takes in two booleans and it will return true if both are true, and then otherwise it will return false. So let's get into that. And hopefully I do well in typing while looking up at this gigantic screen. So we want our type to be called, oh, and there's even input lag, that's great. We want AND, so we want to take in two types, and then we want to make sure, so if T extends true, we also want to, at that point, check if U extends true. And if this is the case, then this is true. But if it's not the case, so if U is false in this case, we would return false. And then otherwise, if T is false, that would also be false. So in either one of these cases, if either one is false, then it's false, and if both are true, it is true. There's only one case where it can be true and two where it could be false in this case. So showing it off an example of that, we could say add false and true. And this one, oh, okay, I called it add instead of and. Okay, so here we get false because they're not both true. And if I change this one to true, then we get true. But as we've seen before, if we pass it anything else, we'll get false. Because we're allowed to pass whatever we want in here, we haven't constrained essentially anything can be passed in here. So what we need to do for this is to constrain these to Boolean. So T must be assignable to Boolean, and U also must be assigned a Boolean. So now we get a type error that says this is not allowed, so we need to then pass it anything that is valid, so that is false, true, or Boolean itself, which would, in our case, not be particularly useful, but you could do it. That all make sense? Any questions? Okay.
I have one question. What was
Yeah.
the name of that operator again with the caret and question mark?
Oh, the 2/.
2/?
Yeah.
Okay.
Mhm. Okay, so going back through here. So here is the example. Not sure why this suddenly does not fit on the page, but that's fine. This is pretty much exactly what we put, so we're all good to move on from there. And also keep in mind, all of these types that we are making will be relevant for later. We'll be using all these for our final edition. So here we have map types. So we more or less map over all of the keys in an object, and we can do things to their values. So in this case, we have, we take every single value and we replace it with cheese. So here we have a favorite food in this object here, favorite food, favorite child, and then this gets turned into cheese. And this also works the same for arrays, just like how in JavaScript arrays are also objects. Here they work very similarly for this case. That makes sense?
So the key in key of T is just iterating through all the keys of type T. Is that what it is?
Mm-hmm.
Okay.
Yeah, key in takes, like this right part here, key of T can be any union. We could pass it a union of different things, and it would maybe create that, but key of T is just saying all the keys of this, which in this case is favorite food and favorite child. In this case, it is 0 and 1.
Okay.
To map over all those keys.
Okay.
Mm-hmm. So here is variadic tuple types. So, oh, I know why this doesn't fit on the screen anymore. It's because I have a smaller monitor. That makes sense. Or maybe this is a gigantic, humongous monitor and it doesn't work. Oh well, I definitely didn't test on a gigantic TV, so who knows. We can scroll, that's okay. So yeah, so variadic tuple types. The one that sounds very scary, but actually is not that much. So here, we ultimately do not care what's inside of the arrays. We just care we have arrays, so we say unknown of, it's an unknown array of unknown. We don't know what it is, we don't care. So we're going to take these and we can use variadic tuple types. We can do something similar to the spread operator in JavaScript. It'll spread the tuples into another tuple. We must say that it is an array, otherwise we'd not be able to spread it as so. So in this case we have garlic in a tuple and bread is scrumptious. So here we spread them both into one tuple and we get garlic bread is scrumptious as a type. And we have infer. There's way too many use cases for infer, but we'll go over one or two relevant ones. So here, for example, we have type element, which grabs the type of a array element. So we can infer the item here. And we know for a fact this must be an array because we have said it must be to go into this type. And here, this never case will never happen, but never is our bottom, so we just put it here. We could put literally anything we want, but it's here to be not confusing. So here, we find out what type the elements are. In this case, the elements are number. So here's a different use case of this. We could then use it to get the last element out of a tuple type. So here we're passing 1, 2, 3, 4. 4 is the last element. Here we don't have a last, so we use our default, which is 42. So we're saying if t extends this, which means does it have at least one element in it, it'll take all of the elements before the last element and put them in this underscore variable, all to say we're not using it. So, and then our last will be put in L. So if it does match this, we get L, which is the last element, otherwise we get the default, which in this case, we have default to the default to 0, but you could pass, like here we have 42 as a default, we could change that. Does that make sense? Any questions here?
Can you just scroll over to the...
Yeah, this is just a bracket.
Oh, okay, okay.
Mm-hmm. I wonder if I can... Nope, that did not help me. Yep, but that makes sense otherwise, or any questions?
So is infer, is that the type we previously defined, or is that just what we're calling?
Infer is a keyword.
It's a keyword, okay.
Yeah.
Okay.
You must be using you must be in a conditional to be able to use infer, but in this case, we're just saying we would like to somehow define some type or some piece of this. So in this case, infer refers to all of the elements before the last element, which is inferred here, and we assign those two variables. And then if we take the last example, we're saying we want to infer whatever item is inside of an array. So if this does match, then we assign item and we can use it in the true clause. If it does not match, then we can't access it because it did not match.
Okay.
It's a really confusing one, I would say, because there's so many use cases for it, but it's one of those ones where you just have to know. We'll come into it, it won't be anything too far off from what we've done here. So you should be able to understand if you understand these use cases at least.
Okay.
Mm-hmm. So another exercise pop. So we want to take in a type, which is a tuple, and return a copy without the last element, which is very suspiciously similar to this, except for changed up a little bit. So let's get into that. Is this deciding to... Okay, it just wants to be half screened. Okay, there we go. So if we want something like, what did we want? We wanted pop, right? I think so. Yeah, because we just did last. So for pop, we want to take in some array. So we remember we must constrain it. So we're going to extend unknown. I need to spell unknown correctly. And t extends unknown, and if t extends, and we take our tuple type, and we want to then infer these items. So if we want to infer we can call it head, something like that. And then otherwise we want to infer the last element, which we can just do as an underscore, because we do not care about it here. And if this is the case, we want to return head. Otherwise, we want to return something else, which in this case makes a lot of sense to call an empty tuple. If there's no more elements to pop out, we can just say this is an empty tuple. So giving some examples of this one, we can pop out something 1, 2, 3, 4. And here we have 1, 2, 3. And if we then take this and get rid of all of our items, then it's an empty tuple. That all make sense?
Interesting.
So this is pretty much exactly the same as our last example, except for we cared about the first elements instead of the last element. So grabbing this back, here is our pop, which is again pretty much exactly what we did before. I even had the same example of 1, 2, 3, 4. Amazing. Not a very unique example, I know, but interesting that I've not deviated too far so far. But now, at this point, we know everything we need to know to be able to add in the type level. At least in language feature wise. So how could we add some small numbers together? We could do an addition table, we could have a bunch of arrays that essentially have indices there. So we could have like 9 and 9, index 9 and 9 gives you 18, for example. But that takes too much time to type and it's not as fun as the other example, so there actually is a length property on these tuples, which is accurate if you have a literal like that. So for example, here we can grab the length out, but here we can say we want a tuple of length n. So once we get that tuple of length n, we can then concatenate together like we did in the example before with the spread. So if we then spread both those together, get the length again, then we have essentially added up those numbers. So to get our tuple length n, again in the type level, we do not have anything like a for loop or a while loop, so we have to use recursion to do this. So we're taking n, which is our number, and we're saying if it is the length, we're going to stop recursing and give back our array or our tuple, sorry. And if not, we are going to put everything else we've had into an array, into our tuple, and then add never to it. Never is just a sentinel value. We don't actually use it. We only care that we're filling up slots. So here we're just going to keep recursing. So like we want a length of 2. We would start here. We would say, okay, 0 is not 2. So we would continue on. We would take our nothing out, put it into a new tuple, add never to that as well. Our length is now 1. Then we go here, do that again. Our length is now 2. And then once we finally hit that, we now have a tuple of length 2. Then going through here, we create 2 lengths here, and we stick them both together, and then there we go. Does that all make sense?
Not gonna lie, I got a little lost on that one.
I think that's fine enough. Which part was confusing?
Oh gosh, just the whole recursive aspect of using it to derive the type. I'm just trying to
Yep,
get my mind around that.
I agree. That's definitely confusing. Recursion will be a big part of the rest of it too, because there's no other way to loop through anything. But essentially, we just have a base condition. So like as if this were a for loop, we would say while n is less than the length we want, or
Right. I'm
this is
on there.
Yeah. Okay. Just how exactly it works is confusing. I think that'll be a lot of this though, because like everything in here is like, how does this work? Unless you played around with it a bunch. But yeah, otherwise, our limitation is 999 per tuple, because there is a recursion limit here, which makes sense, because otherwise if you have infinite types, you're gonna have a bad time and break your LSP. So we have 999 as our limitation. We could end it there, say, okay, great, we have added up all the way up to like 1998, somewhere in there, I think that's the number. But that is no fun, so we will continue on so we can add numbers that are bigger than the actual numbers themselves can hold. So, going on from here, we need to now go back to grade school, do some addition. So essentially, we need to start at the right side of the number and start adding from there. So here we have 5 and 6. And we need to add our carry, which in this case we don't have a carry, it's 0. So we add 5 and 6. We put the rightmost digit from 5 plus 6, which is, we have 11. We take 11, get the digit out of that, the ones place, and put it down here. And then we take our carry and move that onto the next. We have 1 for a carry and then 1 and 0. Add those together to get 2, and there we are. I forgot to mention, we have to know how to add numbers to follow this talk as well, but I figured most people know how to add numbers, so hopefully that made sense as well. So how could we do something like this in code? Here's some more JavaScript-y syntax to hopefully make more sense, and so we can avoid a lot of the weird implementation details that we have because we lack things like the remainder operator or division or addition in the first place. So here we would take our results while we have numbers to add. So like while we have a carry, well, there's numbers left in the first number, the second number to add. We're going to keep looping and we're going to add those up. We want the last element, the last number, and we want to add those together along with the carry. And to get our digit, it's just the remainder there. And to get the carry, we want to divide by 10, and this would be integer division here. And from there, we push the result, and then we move on with our new carry value and continue on. So like in our example before where we had 16, I think we had 16 plus 5 somewhere in there. So there we would start out, we would get the last digit of 16, the last digit of 5, which is 5 and 6, and our carry is 0. And from there, that gives us 11. Our digit would be 1, and our carry would also be 1. And from there, we push the 1 that happens to be the digit to our result, and our carry is now 1. Then moving on from there, we essentially move on to the next number, which is 1 and 0, because there is no extra number on that other one. So in that case, we have 1 plus 1, and the digit there is 2. And there is no carry because there's nothing in the tens place. And then we push that, so we have 2 and 1. And from there, we have nothing left to add, so we finish it out and convert that whole thing into a number, which would be 21. Does that all make sense? I feel like this one's hard to visualize a little bit.
I'm with you on that one.
Okay. So, how could we split into digits on the type level? And because it goes off the page now, the only thing to the right of that is just right brackets to close them out. There's nothing else there. But what we can do is we can use something like a template literal to turn it into a string. And from there, we can split it into different digits. We'll get into that on the next slide, how those work. And then map nums, that would be a map type that maps it to a number, which we will also get to there. So for example, here we have 2, 8, and 9. That turns into a tuple of 2, 8, and 9, exactly what we need. And then that way we can go right to left and start adding things together. So here we also have a num-like. Since we're stringifying, we could have a string, we could have a big int, we could have a number. So there's no need to constrain ourselves to only adding numbers up because they would all work essentially the same. So here is our split. We're using another usage of infer. It's a little bit different and wacky here, that it works slightly different, but more or less it's around the same as before. You can kind of understand what's happening here. So we infer the head. The head is the first number in here, which is 1. And then we have the rest, which is 23 at that point. And we put the head in our array, which starts out here, and then we continue on recursively, splitting the rest until we don't have any more to pull off. Once it's empty, we have an empty array that gets spread to there, and we end up with 1, 2, 3. That makes sense? Okay, so moving on from here, mapping our numbers. This is the same kind of template we had before for k in key of t and whatnot, except for instead of having a literal here, we take our key, we get our value out, and then we turn that into a number. To a number, we're gonna say is magical. There's some magical stuff we can do to get it to work, but implementation is ultimately not important for right now. But we have 1, 2, 3, that gets turned into 1, 2, and 3. So once we put it all together, we first stringify it, split that into the numbers themselves, and then we turn those strings into numbers, and then we have an array of the digits.
So to-number and map nums, these are like baked into TypeScript, or are these?
This one is not built into TypeScript. This one's defined right here.
Oh, sorry.
But to-number is also not baked in, but
Okay.
I'll show it off later.
Okay.
But it's another one of those things where it's just like a magic trick you have to know,
Gotcha.
or else you'll never guess how to do it.
Okay.
So we'll get into it around the end. I'll show it to you.
Okay.
But does that all make all sense without?
Yeah.
Okay. So getting into here, carries. Again, just like there's no division operator in the type level, there's also no remainder operator, so we have to do this ourselves. So here we want to get, so whereas we had 2 here to get the first digit, if we want the second digit, we have to pull off 2 of these. Also, this is a weird rendering bug. Why does it do that? I don't know. But there's backticks here that should not be here. So pretend these 2 backticks don't exist. But otherwise, we can stringify and say, okay, if there's 2 digits in here, then that means we can pull that off and turn it into a number. If there's less than 2 digits, then at that case we say 0 because there's nothing to pull off. So if we have this here, we get the carry, it is 12. Or sorry, it is 1 for 12. Does that make sense? Okay, so moving on to get digit. We could do it in a similar way here, but instead here, let me scroll over a little bit. We're going to turn it into a string. We already have split and we already have last. We already defined those, so it's pretty convenient. We just split it up and grab the last one and turn that into a number. So we first turn it 12 into a string, then we split it into 1 and 2 as strings, then we grab the last, which is 2, and then we turn 2 as a string into a number. That makes sense?
Yeah, that makes sense. That
Okay.
kind of reads like English. When you,
This one's
yeah.
a lot more convenient to do this way. And luckily we've already gone over what all these types are, so we don't have to scroll through some more slides. There are some fancy utility types out there, or like utility libraries that would help if you so chose to do stuff like this on your own, but we're doing it all from scratch. So yeah, like I mentioned before, there's no fancy looping stuff built in. We have to use recursion. So in our case, our base case of when we stop adding is when we run out of digits to add. So we're using our and type before, and there's an is 0 type which just says true if it's 0 and false if it's not. We just want to know if the length of these tuples is now 0 because we have popped everything out, and carry is 0 because there's nothing left to carry. And if that's the case, we can stop recursing. So throwing it all together, the most complicated slide there will be in this entire thing is this. So we're gonna say, once we finished out, it's true, we end out with our empty tuple. Otherwise, we're doing all this fancy stuff. So sum here is always going to be defaulted. We're not gonna pass it anything, it just makes it nicer to read this way. But we default it to adding all the digits together, which is carry the last of num1 and the last of num2. I'll scroll over to show you that. So it's just adding the last digit of num1, num2, and carry. And then from here, we want to go through, recursively call this. We want to take out those elements we just added by popping them off. And then we get the carry from the sum and get the digit. And we pass both of these back through here and keep going. So for example here, we have our adder, we have 2 and 4. We start out with our tuples. We grab the last element and our carry is 0. So we go through that same logic again. 2 plus 4 plus 0 is 6. Then we take this item here. We take our 6, we grab the carry, which is 0. We grab the digit, which is 6, and pass it back through after popping these off. You'd continue through. So like there's 6, 6, and 6, so I won't bore you with going through all of those. But then we have 5 and 9, which is a little bit of a different case. So we have 5 and 9. Our carry at that point is 0. So from there, we add them up. We get 14. We get the carry, which is 1. We get the digit, which is 4. And in that case, we have nothing left in either one of these, but we will continue on with our 1 as our carry. And then we have 1 plus 0 plus 0, which ends us out with 1, 4, 6, 6, 6. So that is why, one of the reasons why it was very convenient to default our last to 0, because we don't have to handle a case where it's not in there, we just default it to 0. Very helpful, very fancy. Any questions there? This is like the crux of it all.
No questions from me. This was didn't expect to think this hard this afternoon.
It is. I went for something that makes you think very hard because I've seen, I don't know, lots of talks out there that are like, let's learn how to use Copilot. And I'm like, I have seen enough of those. I want to do something that makes you think really hard. So here we are. So here we have some more stuff. So I guess I'll just scroll that over for now. So our final type add, first we grab all the digits out of M and N. We've seen digits already. And then here we have a wacky thing to get over the recursion limit, which is extends infer r extends number. It doesn't matter what this does exactly, it just helps us get over the recursion limit. It's a fancy little trick in there, but you could essentially think of this as instead of having this infer r, we just pass adder digits n right where r is. So yep, more or less what we're doing is we are adding up both of these. We get arrays of digits for both numbers. We then add them together into an array. Then we join them together and we turn them into a number. And that is that. That's everything there is to know about that logic. Any questions on this one? Okay, so let's take a look at that code. We can look over any of the things we omitted for brevity. Why does it want to show only half of the screen? I do not know. But getting into here, you can see here this works with anything here. Like we could do numbers, we can do, well, this is a big int, this is a string, these are numbers. We could pick whatever else we want, and we can get so big that it gets through the limit of integers as a whole. So it works pretty well, but then at that point, of course, it's not accurate because integers cannot hold numbers that big. But it does accurately add very big numbers now. And we could probably convert to work with big ints and return a big int, so we could do ridiculously large numbers around that. But as an example, we mentioned, I think it was to number. So let's take a look at that one. So to number here is another wacky one. We're just saying weird stuff out here, but more or less, it's already a string. If the string, we can infer and that like there is a digit here and it is a number as well, then we're gonna say it's a number, otherwise we say it's never. So it is possible for this to return never, but that's how we can convert that string into a number by doing this. So we have 1, 2, 3, that gets turned into 123. And we just need that for our final result to turn that back into a number. But yeah, other than that, is there anything specific you wanna look at, try out, play around with?
Does this just work with integers, or can it handle like floating point as well?
This only works with integers, but I'm sure you could make it handle that somehow.
So that's an exercise for the listener.
Yeah, exercise for the reader, definitely try it out. Yeah, I wonder, because then in that case you don't even have like a big int to handle the precision, because you would only have like 64 point double to handle your floating points, so who knows. I'm sure it would break. I can try it out. I can almost guarantee it'll break because there's nothing handling the dots.
Okay.
But yeah, anything else, or just look through everything one last time?
This was really interesting. I learned a lot, so thank you.
Yeah, I still have a little bit more, but let's just give it a scroll through. And I do have all this on GitHub, and I have a link to it at the end if you ever want to play around with it. But it is very nice and interesting. So yeah, we went through all of these. Here's some more of our utility types. We already looked at last, we already looked at pop and map nums. I don't think we looked at join, but join's also pretty similar to everything we've done. I'm sure we could figure it out if you've seen the rest. Just more fun recursion, but instead of turning it from a string to an array, we turn it from an array to a string. And then we have our and I think digits is the only other one we have in here. Yeah, I think that's pretty much it for here. We've seen pretty much everything. But yeah, for our final question, the inevitable question, can we actually use this? Because I did mention it's impractical, but how would it look if we actually tried to use it? Should we even try? So you can use it if you want, but it only works well if you know the literal types. So if you compile time know the types, or you do some ridiculous assertions. So for example here, we can make an adder function that does work correctly if you happen to know the literal. So here it's pretty much the same, except for we have to cast it as the type we made, which is add, and we have to force these to extend number, so we can pass these in as an argument. But we have to cast because, understandably so, x plus y, when you add two numbers together, it gives you a number. It does not try to handle any kind of literal stuff in here. So it does work. Like here we have add, and we have 5 and 10. It infers it correctly, and we get 15. So we can see the exact return type. Here's the signature we get out of that. But however, if we have something like a number we don't necessarily know at runtime, we end up with never, because we do not handle the case where we don't have a literal to deal with. But in that case, we could do a ridiculous assertion to figure that out. We could say, if number equals 10, if number equals 11, and so on for every number it could possibly be, then you could use this. And why would you want to do this? You probably wouldn't. I remember I tried it I made an is-even function in Rust, but it was like more or less checking like if it's 2, if it's 4, if it's 6, and so on. And even doing that for like an 8, I think it was probably like a 32-bit integer. No, it probably did 16-bit, but there's like, it's so much code to write out, and it's so much runtime overhead to get this to work that it is almost definitely not worth doing. But it's a fun exercise nonetheless. Any questions on this part? Okay. So some resources, like here is the GitHub repo. So all of the code you saw there is available to you if you want to play around with it. I guess one note to say is that this is reliant on using the latest version of TypeScript, because if you go back to TypeScript 4, then you have to do some more things to handle the recursion limit and other things. So some performance things were added somewhere in there. And otherwise, this part was part of this challenge itself, like adding numbers, is a part of a repo called Type Challenges, which I really enjoy. It has a lot of different stuff like this. So like you could do more reasonable things. This one is marked as level extreme on there. So
okay.
yeah, you can do it if you want, but there's easier ones out there if you are not interested in going through all of this in a day. But I found that very helpful to learn a lot more about how types work. So like, I think you had mentioned like some of the utility types. So like a lot of those challenges are like, how does exclude work? How does omit work?
Okay.
And those ones are fairly simple once you understand how the conditionals themselves work. Otherwise, the best way to learn about any of these types is, or how these things work, is the TypeScript handbook. I just ended up reading it front to back because otherwise it's pretty hard to find a lot on this, because like I mentioned before, most people aren't particularly into looking up half of this stuff because it's maybe not relevant to them. If you're a consumer of the types, you ideally should not have to think about it too much. It should just infer and work and be nice. But if you're writing a library or doing something like this, you'll need to know. And then otherwise, a really fun example of something else ridiculous built in the type system is someone built a WebAssembly runtime in TypeScript, so they were able to run Doom in the TypeScript type system. It took multiple days to compile one frame, but it does work correctly.
Wow.
They had to build like pretty much an operating system and the whole thing, so that is a good thing. Definitely recommend checking that one out. It's a fun watch. And sadly, maybe there isn't any like fancy type shenanigans. It's just a lot of like raw implementation of things that you would not expect to implement when you're doing anything like that. But yeah, that is all. Otherwise, if you want to connect with me, look at my blogs and whatnot, jacobasper.com, that's where it's all at. But yeah, anything else or?
Thank you, Jacob.
Yeah, no problem.
Appreciate it.
Thank you.
Then I think we're probably good.